Hello, welcome to the third part of our series of tutorials on sequential Monte Carlo samplers, which we're making as part of the Centre for Doctoral Training in Distributed Algorithms here at the University of Liverpool. So in the previous two videos, we've said we are interested in estimating things associated with this probability distribution, which we're calling the target, and we've drawn an example 1D target in red. And so far, we've essentially just done standard importance sampling. So we've generated samples from some kind of proposal, which we've denoted Q, and we've imagined a situation where they've landed on this axis somewhere, and we've noted that some of them have landed in more useful places than others. So, for example, these three are in regions of higher probability density of the target compared to the surrounding four. So in the previous video we said, well, if that happens, then you can do what's called resampling. And essentially what will happen if you do some resampling is it will remove these samples that are not very important to us, probably, and it will probably generate lots of replicas of these samples which are in a more important region. So while that generates replicas and removes these pretty much useless samples, we know that it doesn't actually help us explore this space anymore. So we finish by saying that this is really the first iteration of a sequential Monte Carlo sampler. So I'm calling this proposal Q1. I've given it a subscript 1 now so that we know it's iteration 1. And in iteration 2, what we're going to try and do is explore this bit of the space more. And we're going to do that by proposing new samples that are generated randomly but centered, in this case, on our samples from iteration 1 that are still left over after resampling. So, like I say, we're doing that to try and explore this bit of space a bit more. So the first thing to be aware of, really, is that I am being quite casual with notation in all of these videos. And it's deliberate, really. It's because these videos are supposed to be, hopefully, a relatively friendly introduction to SMC samplers. And if you want to get really into it, then there's academic papers that will do that for you. So it's kind of supposed to fill the space between not knowing the subject at all and reading papers about it. So, for example, I'm going to use Q1 to denote our first proposal distribution. What we're talking about here is we've proposed some samples and then in fact we've done resampling as well. So technically you might argue that Q1 is the original proposal and then it's been through a resampling procedure, and so you need a different notation to represent this distribution. And of course you'd be right, but for now I'm not going to bother, basically, for the sake of simplicity. So I'm just going to say Q1's our first proposal distribution, and there may or may not have been resampling. So we know we've got our initial set of samples. So I'll use a subscript 1 now. So we generated 1 to n of those, and they came from Q1. So now we're going to generate a second set where we say that x2, our ith sample, iteration 2, it's come from some other proposal, which now is conditional on our ith sample of x1. So to get to this point, we've used this simple drawing to motivate what we're doing, basically. So we've said, well, we think that this region is important, but we just have repeated samples here after the resampling procedure. Then a sensible thing to do at this point might be to propose a new set centered on these. So Q2 could just be a Gaussian whose mean is equal to your ith sample from the first iteration, i.e. it could be a Gaussian centered on one of these crosses. So I say that because we've got this example to motivate what we're doing, but of course these proposals could be much more complicated. But a Gaussian will do for now. So remember that the goal here is to estimate some expected value of some function for the target pi, which is equal to this integral of the target. So I'm going to use x2 here to be consistent, multiplied by f of x2. So we've got our second set of samples. So we might think at this point that we could just do standard importance sampling, which we've already seen. So in other words, we would rewrite this integral to be an importance weight multiplied, function of x2 multiplied by f of x2, and then multiplied by our proposal for x2, where, as we've seen before, this importance weights, the importance weights will be given by target divided by proposal. So target, proposal. Okay, so perhaps that seems fine, but then our question is, what do we write for this? So if we want to find our proposal for x2, we have to remember that actually we've generated a load of samples at iteration 1. We've then gone on to generate another load of samples at iteration 2 that were conditional on those that we had at iteration 1. So if we want to find a general, our proposal in iteration 2, we can only do that by marginalizing over, so we've had our q of x2 given x1 and our q of x1 marginalized over x1. So if you wanted to do this, then you're going to need to be able to compute this marginal distribution. And okay, if you choose these quite carefully, then perhaps you can evaluate this integral, but in general it's going to be very difficult, if not impossible. Particularly, for example, if resampling has happened between iterations, or if you just have a more complex proposal. So in general, we're going to say that this integral is intractable. So we need to think of a different approach. So instead, we think, well, we have generated samples over 2 iterations. In this case, where we're looking at a 1D target, then we can imagine that actually what we're doing is we're targeting some kind of 2-dimensional target. So we might have our samples at x1 and our samples at x2, and we plot one against the other. Then, as you would expect, they're in some kind of 2-dimensional space. And then you could imagine that actually you're interested in some kind of 2-dimensional target, which I'm going to write as pi j. So j to represent joint distribution between x1 and x2. And then we're also going to say that actually the thing we're interested in is the marginal of this joint distribution. So we're going to imagine that if you integrated this joint distribution, over x1, then we're going to be left with our original target, x2. Okay, so how does this help? Well, if we go back over here, and I'm going to delete all of this because we know it doesn't work. Okay, So we're going to sort of revisit this integral, and now we're going to use our sort of knowledge of that. We've kind of invented that joint distribution. We're noting that this is the same as this integral, and now I'm going to replace this pi of x2. We know that this is the integral of joint distribution, which is defined over x1 and x2, integrated over x1, so marginalised over x1, multiplied by, as usual, f of x2 here. And then just moving the integral around to help us see what's going on. Here's our joint distribution. Here's f of x2, and then we have a dx1, dx2 at the end. Okay, so now we're going to follow an importance sampling procedure again, but now we're targeting this two-dimensional joint distribution. So we end up saying that this is equal to, we're going to say now importance weights at iteration 2, and that's a function of x1 and x2, multiplied by f of x2, and then our proposal, which, as we know, is samples at iteration 2 conditional on those at iteration 1, and our samples at iteration 1. So we're still doing importance sampling. It's just that now we're targeting this 2D joint distribution, and our proposal is this thing. So these weights here, so if I take a closer look at these, and the weights at iteration 2, x1, x2, are equal to target, which is now the joint, defined over both x1 and x2, divided by this proposal, x2 given x1, and our proposal over x1. Now the question at this point is probably, well, what is this? What is this joint thing? And this bit, well, I find anyway, certainly the first time I looked at SMC samplers, is quite hard really. It's quite difficult to understand. That joint distribution, actually, we can pick it. It can be anything we like, just so long as it marginalises to be the target, which is what we've written here. So what I'm saying is, we go from this step to this step. We say that our target is the marginal of this joint distribution. It doesn't matter what this is, as long as it's a valid probability distribution and it marginalizes to become the target, then it's up to us, basically. It can be anything we like. So one of the things that we're going to try, for example, and this hopefully it'll become more obvious why in the later videos, is going to pick this to be our target multiplied by another probability distribution that's going to be written with an L, that is conditional on x2. So its argument is x1 and it's conditional on x2. So obviously if you integrate this over x1, then you're left with the target at x2, which is what we want, that marginalization property. And then this L can be anything we like, basically, and we call that an L-kernel quite often. So, like I say, this bit's a bit tricky, really. So just to be really clear, we've been through this maths to show that we can, instead of targeting pi of x2 directly, we'll actually target this joint distribution so long as it marginalizes to give us pi of x2. And that means that we can pick that joint distribution so long as it has this property here, and we're going to define it as pi of x2 multiplied by this L-kernel, where the L-kernel is ours to choose. It's a probability distribution, but we get to choose what it is, and as we'll see later, it actually has quite a serious impact on how the algorithm performs. Okay, so once we're comfortable that this is the joint target distribution, then our weights at iteration 2 as a function of x1 and x2 are now equal to our expression for the joint, which now has this L-kernel, x1 conditional on x2, divided by our proposal. Now, all we're going to do at this point is remember that our weights at iteration 1 where this was standard importance sampling, so that was just equal to the target at x1 divided by the proposal, our first proposal. And so substituting this into here, so replacing q1x1 basically, we end up with our weights iteration 2 equal to this kind of ratio, so it's pi at x2 pi at x1, i.e. target at x2 divided by target at x1, our L-kernel, and then our second proposal, all multiplied by the weights at x1. So now we have an equation for sequentially updating the weight of our samples x1, x2, given the weights of our samples at x1. So, and you can imagine you can extend that to further iterations, which we'll do in the next couple of videos at some point. But basically, the kind of take-home message from this video is we've entered a second iteration. We want our samples x2 to explore the space a bit more, and to do that we're proposing them conditional on x1. We're still interested in this sort of expected value of some function with respect to the target. We go through a bit of maths and we say, well, actually we've got some freedom in choosing this joint distribution, so long as it marginalizes to give the target, which is what we've written over here. We've chosen it to be the target multiplied by this L-kernel, where, like we say, the L-kernel is completely up to us to choose. And then, yeah, that's the difficult concept, really. Once you're comfortable with having chosen this as the target, then it's just a bit of maths to show how the importance weights are updated in iteration 2. So that's we're definitely getting there, but the real question is, well, what's this? We said it's up to us to choose, but okay, what should it be? And so this is what we're going to look at in the next video. I think probably the way we'll do it is we'll look at it in a bit of a hand-wavy way first, using some pictures, and then probably in another video we'll go into the maths. But it's a parameter that we need to choose, this probability distribution, and that's something that's different, I'd say, for sequential Monte Carlo samplers compared to, say, something like Markov chain Monte Carlo. It's the fact that we have this extra thing to tune or pig.